So in this video, we're going to be looking at how we can predict whether a reaction is going to be spontaneous or not from looking at data as well as a graph as well. Now, starting off, we're asked to explain why this exothermic reaction is going to be spontaneous at low temperatures but does not occur at very high temperatures. But we've got to think about this in terms of the kind of subjects in our delta G equation. We know, of course, the reaction's exothermic, so delta H is going to be negative. We also know from the reaction, because we're not given this value, we can only estimate it, that we've got 3 moles of gas turning into 2 moles of gas itself as well. Now, in terms of this, we know delta S, therefore, that is going to be negative itself as well, because entropy is going to be decreasing. Now, if you were to look at our Gibbs energy equation, we've got delta G being equal to delta H minus T delta S itself. Now, we've got to think about this in terms of negative numbers, negative terms, and positive numbers as well. Now, I'm just going to pick a value. I like to use minus 10 for the enthalpy change, just to estimate it, and then we're going to subtract a value for temperature. Let's start off with the low temperature to begin with, where we know we've got something like 1 Kelvin. And then, of course, delta S, I'm just going to pick a value which is going to be minus 1, because that's quite easy to work with. So we've got 1, and then we've got times by minus 1 itself. Now, when we look at this, we've got minus 10 subtracting 1 times minus 1. In that bracket, we've got a negative number times by a positive number. So overall, the actual number within the bracket is going to become a negative number overall. So what we're doing is we're subtracting a negative number, and so we're technically adding it. Now, if we did that, we would end up with a value for delta G, of course, being in this case negative 9. Because we're technically taking minus 10 and adding positive 1. Now, of course, delta G at this very low temperature of 1 Kelvin, we know it's going to be negative, and so the reaction is going to be feasible. So this reaction is going to be feasible at low temperatures. Now, what about if I were to look at a higher temperature? Let's say if we had something like 100 Kelvin, well, I'm going to have negative 10 again, and so we're going to be subtracting a value of 100 times by minus 1 in this case. And so if I were to simplify that, technically, I'm subtracting minus 100 itself. Now, technically, that means I'm actually going to be adding 100, positive 100, and so what I end up with is, of course, positive 90. Now, of course, at lower temperatures, we know that delta G is going to be negative, and so the reaction isn't going to be feasible. The temperature is going to increase, so that T delta S term over here is going to increase, and so we know we end up with a positive value overall at a certain point. But in this case, you can see I've got positive 90 itself. Now, what about if I were to explain this in the exam, because the mark schemes vary every single year and they want something different every single year? Well, here's how you can get the marks every single time. This is what you need to be able to say. First of all, delta G is going to be negative. Why? Because you've got an exothermic reaction. Delta S is also going to be negative. Why? Because you've got 3 moles of gas forming 2 moles of gas. Now, what does that mean in terms of T delta S? Well, that's also going to be negative. Now, after we've talked about those 3 terms, we need to talk about what happens at higher temperatures. Well, at high temperatures, T delta S, that actually becomes more negative. It becomes more negative than the delta H value, and eventually it actually outweighs the delta H value. Delta G is overall going to become more positive, because we're taking a negative number and we're subtracting a negative number already, and so the reaction is going to become unfeasible eventually. So yeah, that's how we kind of lay it out in terms of the exam. Of course, this is the wording that we go for to get the maximum amount of marks itself. Now, moving on, I've got a table for you to have a look at using the same principles again. I want you to decide whether we've got a positive or negative delta G sign, and whether the reaction is going to be feasible for each of the following conditions itself. Feel free to pause the video, have a go, resume once you're ready to go over the answers. So yeah, again, we need to look at this in terms of delta G, and of course our positive and negative values of delta H, and then of course our delta S value combined with T. So yeah, looking at the first one, we've got a negative value for delta H. So let's say we've got something like negative 10 again. For delta S, we've got a positive value. So again, let's say we've got a value of positive 1 to begin with. So of course, we've got 1 Kelvin times by 1, and we're going to be subtracting that itself. Now, I end up with, in this case, a value that's going to be minus 11. Now, in this case, you can see temperature is going to be, of course, a positive value. Delta S is positive as well, but temperature is going to be very low. Now, of course, course temperature can only increase, and so let's say if I had 100 Kelvin, 200 Kelvin, 300 Kelvin, doesn't matter what we get, because we've already started with a negative value of -10 and we're subtracting a positive value that could be anywhere from 1 to 100 or 1000 or whatever it might be in terms of the highest temperature we can get, we're always going to end up with a negative number. So the reaction in this case, if delta H is going to be negative, delta S is positive, will always be feasible. We're going to be taking an already negative number and subtract a positive number from that. So the reaction is always going to be feasible itself. What about the next one then? Well, we've already looked at this example over here, and we said, of course, if you were to deal with a negative delta H, negative delta S, again, let's see if I've got -10 and I'm subtracting a value of 1 times by something like -1, we would end up with a value of something like -9 in this case. Now, because we're subtracting a negative number of -1 overall, because that's what we'd get over here, 1 times a -1 gives you -1, we're just going to end up with, of course, that negative number becoming less negative. So it starts off negative, yes, at lower temperatures we know delta G is going to be negative and the reaction would be feasible, but when temperature increases, eventually this value over here, the T delta S term, that's going to override that delta H value, and so at higher temperatures we end up with, of course, a positive delta G, and so the reaction is going to be unfeasible. It's not going to be feasible. Yeah. What about the next one then? Right, so we've got lower temperatures, higher temperatures over here. Well, let's look at our value of delta H, and let's imagine that's going to be +10, and we're going to be subtracting our temperature of 1 times by entropy, which we're going to say is +1. Now, of course, this will give us a value of 9, so we know at lower temperatures we're going to end up with delta G actually being positive itself. But then, of course, let's say if I were to change my actual temperature itself but keep everything else the same, and let's say if I were to have again delta H being 10 and we're subtracting a very high temperature of 100 times by, of course, 1, we're going to end up with, in this case, a value of -90 itself. And we can see delta G eventually is going to become negative. So in that case, delta G at higher temperatures is going to be, of course, a negative value. So of course at lower temperatures we know the reaction is not going to be feasible, and then at higher temperatures we know that the reaction is going to be feasible itself. And one word that you might prefer to use rather than unfeasible would be, of course, just saying not feasible itself or not spontaneous. Looking at the next one then, so the next one again, it's very similar to the first one that we did. Of course, let's say if we were to deal with a value of delta H being positive, so I've got something like 10, and then I'm going to be subtracting, right, a negative value. So in this case, I've got a temperature of 1 times by, of course, and then it's going to be -1, something like that. Well, if we're subtracting a negative value from an already positive value, what's going to happen is of course we're going to add a value of 1. If temperature was 200, then we'll be adding a value of 200, and so the actual Gibbs free energy is always going to be positive in this case. And so if we ever come across this circumstance where we end up with, of course, delta H positive, delta S be negative, the reaction will never be feasible. So I'm going to change the wording on this one slightly, and I'm going to say it's not going to be feasible, because that sounds better compared to unfeasible, which of course you can find in some mark schemes itself. Again, 10 minus -1, it's going to be, of course, a value of 11. 10 minus -100 is going to be a value of 110 itself. Yeah, so again, that value is going to constantly be positive, and it's just going to get more and more positive itself. Now moving on, what about if we were given some information about a Gibbs free energy graph itself? Now this actually came into the specification because it was assessed in the specification in 2023, and we've got to be aware that, of course, the examiner could give us the equation of course, delta G being equal to delta H minus T delta S, but they could expect us to write this in terms of the equation of a line, where of course we would have delta G on our y-axis, which is what we can see here, and then we're also told that the actual x-axis is going to be the temperature in Kelvin, and we need to be able to rearrange this to get minus delta S as our actual gradient, which is m, and then delta H, which of course is going to be our value for the y-intercept itself. Now how would you go from this equation over here and actually figure out the equation of a line? Well, what I would do is I would say, okay, I've got delta G here, and that's going to be equal to, because that's my y value, y equals mx plus c, that's going to be equal to my gradient times by my temperature, which we know is going to be the x value over here. So I've got my x and y value over here. here, and then I've got that added to something. Now if I were to look at it, right, we've got to think, how can I rearrange this into getting y equals mx plus c? Well, I can see here my temperature is going to be times by my delta S, and if I were to flip that around, technically I would end up with delta G being equal to, and then of course minus T delta S, and then plus delta H itself. Now of course I know my C value straight away would be delta H just based on that. Well, what about my M values? Well, I know it's going to be, of course, temperature is going to be my X value over here, so I could just flip this around, so I would end up with negative delta S as being my M value, so that's my gradient itself. Now of course we need to be able to interpret graphs regardless of if it's Arrhenius, if it's Gibbs free, or even if it's going to be a pH curve itself. And I want you to have a go at the following task, pause the video, have a go at the following, and see if you can interpret the information from the following graphs here. Now looking at the first question over here, we're asked if the reaction is going to be feasible at 298 Kelvin itself. Now if I look at that, how would I answer such a thing? How would I go about finding that information on a graph? Well, we know a reaction is feasible when delta G is going to be negative, and we know delta G is going to be negative, right, from after 700 Kelvin itself, and that's what we can see over here. About 700 Kelvin is when it actually becomes negative. Now of course the actual question's asking us, is it going to be feasible at 298 Kelvin? Now of course that's going to be roughly about somewhere here near 300. Can't really see it properly on this graph, but of course we can see delta G is going to be positive over here. Now of course if delta G is positive, we know the reaction would not be feasible in this case. So in this case, what would we say to the examiner? Well, we would say no, the reaction is not going to be feasible as delta G is going to be positive itself. So delta G is going to be above 0, or we could say it's positive. So reaction is not going to be feasible. What about the next one? We're asked to determine the minimum temperature, this time in degrees Celsius. Remember, this graph is going to be in terms of Kelvin, at which the reaction becomes feasible. Well, we've already kind of done that, and we've said so far it's going to be 700 Kelvin. But remember, to find the actual temperature, which is going to be in degrees Celsius, we need to be able to take, of course, 700, and we're going to subtract 273 itself. Now we do that and we end up with a value of 427 degrees Celsius. So moving on to the next question then, right, feel free to have a go at the following, pause the video and then resume once you're ready to see the answer. So going over this question then, right, we can see, of course, we've got delta H and delta S is what we need to basically be able to calculate. Now, of course, we know our equation is delta G is equal to, and it's going to be, of course, delta H minus T delta S. And what we said before is we can rearrange this to get it in the format of y equals mx plus c. Now, of course, I know my y values, which I can see over here. It's going to be delta G. And then I also know my gradient is going to be negative delta S. And that's going to be times by, I'm going to separate it out here so it's more visible, the temperature, which is going to be my x values, of course, and then my y-intercept is going to be delta H itself. Now if we're asked to find the y-intercept, right, remember the y-axis is in kilojoules per mole, so we know our units is going to be in kilojoules. We've got a y-intercept value of 150 itself. That's what we can see. And so of course, right, I know that delta H is going to be equal to, and it's going to be 150 kilojoules per moles itself. Moving on, because that's one mark there so far. If we were to look at, right, delta S, how would we work that out? Now we can see here, right, we've got delta S in joules per Kelvin per mole, and we need to be able to convert from kilojoules per Kelvin per mole. Now, of course, we know our reaction, we can see we've got a negative gradient, so we know delta S is going to be positive in this case. But of course, remember, the gradient M is going to be equal to negative delta S, and you need to do some further processing like that. So I'm going to select 2 points on here that I think are nice and easy to read. The first one that I'm going to pick is, of course, the one that I've already chosen, where I've got x being equal to 0. So my coordinates is going to be 0 for x, but then my y value, my y-intercept value that I worked out from before is going to be 150. Of course, I can pick any 2 points that are nice and easy to read, and I've gone with this one over here for my first point. I'm going to call that coordinate 1, just like how we do the Arrhenius equation. Now the next point I'm going to pick is, of course, further along the line, and I can see over here, right, I've got a value where I've got x as being 700 itself. So I've got, of course, 600. Then I've got, of course, 650. I've got 700, 750, and then 800 over here. So I know X is going to be 700 itself. I also know my Y value in this case is going to be 0. Now, of course, that's going to be coordinate 2. Just pick any two coordinates, are easy to read. You could have gone with this one as well. You could have also gone with a few others, but we're going to stick with the nice and easy to read ones that land on the square or on edges. So yeah, in this case, if I were to work out a value for M, I'm going to look at the change in Y over the change in X itself. Y1 minus Y2 over X1 minus X2 itself. Of course, you can see my Y values are going to be over here. So I've got 150 minus 0, and that's going to be divided by, of course, my X values, which I can see is going to be, of course, in the same order. We've got X1, which is 0, and we're going to be subtracting 700 itself. So we've got 0 subtract 700. Now I type that in my calculator and I end up with a value of minus 0.124 itself, and of course that's going to be reoccurring. That's my gradient so far, which gets me a mark. Now, of course, that's my value for the gradient, and we know the gradient is going to be the negative of delta S, but we want to find the positive delta S. So in that case, negative delta S is going to be equal to minus 0.124 ... because we're going to keep it reoccurring. So delta S must be equal to positive 0.124, but of course I want to be able to work out my value in joules per Kelvin per mole. Now it's in kilojoules per Kelvin per mole, so I'm going to, of course, times that by 1,000, and then I'm going to round it to 3 significant figures. So in that case, I end up with 214, and that's going to be joules per Kelvin per moles itself as well. And there is my next mark over here.